Good afternoon, everyone, and welcome to this week's live astronomy program. My name is Justin, one of the astronomers at the Science Museum of Virginia, and as always, happy to be your guide during this show, helping you see outer space without leaving your place. If you've watched previous episodes, welcome back. Happy to have you watching again. If this is the first time you've tuned in, well, you may have picked the perfect week to join. We were on an ongoing journey trying to get from the Earth to the edge of the universe, but taking small steps each week. But this week, I think we're at the end of that journey. We should be able to get to the edge of the universe today. But if you do want to catch up with previous episodes, they are stored on our videos page right here on Facebook. And some of the things we've seen over the last couple of months will come in handy during today's episode. It'll save me from explaining a lot of those things again. But before we get started, the usual announcements, I need to thank our sponsor for this series, Allianz Partners. Happy to have them on board. We'll have some links for you in the comments if you are willing and able to continue to support some of the museum's other ongoing missions during this time. Every little bit helps. For the rest of today's show, I'm going to be showing you video created by the same software that runs our dome theater at the museum. It's planetarium software called Digistar 6, and it can do some pretty cool stuff. So I'll spend a little bit of time watching it on a second large monitor I've got off to the side here. If you're able to make this video full screen, watch it on a nice big monitor, I highly recommend it. It'll look a little bit better that way. And as always, if you have any questions that come up during the show, feel free to leave those down in the comments section. I'll try and answer them during the show if I have a spare moment. But again, we're going to try and see the whole universe this week. By my count, this is our 12th week exploring the universe together. So if we head to the edge of the universe today, I think we should be armed with all the knowledge we need to recognize everything we see along the way, or at least recognize it as some normal part of the universe. And surely we won't encounter any big surprises along the way today. So let's get the journey started here. I am going to get us set up in space, switch you over to the nice view of the software here. And I'm sure, of course, that you recognize that. That's been our starting point for most of the shows. And of course, that's the planet we live on. That's Earth. You probably didn't need me to tell you that. But over the first few weeks of the series, we did explore the solar system in a number of different ways. We saw the other planets. We saw dwarf planets. We saw moons going around all of those worlds. We saw asteroids and comets. And of course, we talked a bit about the sun and its influence over the solar system and its gravitational control of all of the objects in the solar system. So that occupied us for a little while. But it wasn't long before we were exploring other planetary systems. Now we have found over 4,000 planets orbiting other stars. And although a lot of these are a little bit different from the planets we have here in our solar system, the range from Mercury to Neptune is certainly diverse. Each one of those has interesting stories to tell us. And most of the planets we are finding outside of our solar system are actually a bit different from any of them in our solar system. The majority of the exoplanets that we have found are in size somewhere between the Earth and Neptune. So they're a little bit mysterious, but if we saw them up close, we'd recognize them as planets. And the arrangement of these other planetary systems is a little bit unusual as well. I'm going to transport over 2,000 of those exoplanets into our solar system and draw their orbits around the sun. So it'd be pretty interesting if our solar system was this crowded. But these are the real orbits of these other planets, as best we can tell from our view here in our solar system. And this is the distances they are from their stars. This is a bunch of planets packed into a very small space. What I'm showing you on the screen is still entirely inside the orbit of Mercury. Now, we found so many planets at that kind of distance from their stars simply because those small orbits take relatively short periods of time for the planets to complete them. We're talking hours and days instead of the months to decades that the planets in our solar system need. And that's largely because of how we find these other planets. I guess that's kind of hard to see on the blue orbits, but most of the planets we have found around other stars were detected using transits, and those are just easier to detect if a lot of transits happen in relatively quick succession. So it's a little bit easier for us to find these planets. They're much closer to their stars, so their transits repeat in hours or days, so that one telescope can see them all. So if all these planets were this close to our sun, they'd be pretty toasty. I mean, Mercury's surface temperature is about 850 degrees Fahrenheit on the daytime side. So most of these planets, you might think, would not be good places to look for life. But of course, we talked about that just a little bit in a previous episode as well. And indeed, a few dozen of these planets are places where we think life might be able to develop. We think the surface temperatures on the planets, with their orbits highlighted green here, could have liquid water on their surface. So we might be able to find life kind of like we have here on Earth. But these, again, are mostly really close to, where our star is. They're all inside the orbit of Mercury again. So to have the right temperature for liquid water, it's a good reminder that they must go around a smaller, cooler star. So I shrunk the sun down for you there. And it's also a nice reminder that, as we got out among the other stars in our galaxy, most of the other stars we encountered were smaller, cooler stars. Now, the color of a star tells us its temperature. I told you that a couple of times. And as we zoom out here across the nearest 20 parsecs or so, that's just over 60 light years, as you'll be able to see here once again. You'll see that this map of stars, courtesy of Jackie Faraday at the American Museum of Natural History, is kind of skewed towards the red end of the rainbow. So more cooler temperature stars means that those are mostly smaller stars as well. Red dwarfs, much more common than red giant stars. So there are the nearest stars. Now, the next picture doesn't really fit into the narrative that I put together for today's show, but I saw it yesterday when it was first released, and I couldn't resist putting it in the show. It does kind of bridge the gap between stars and the next step. This is a picture of a very young star called RU Lupi, and it's still in the process of forming, its system kind of settling down. So this is an infant star system, or an infant planetary system. On the left, you see a disk of dust and gas surrounding this baby star. It's colored kind of red and yellow in this picture. This imagery collected by the ALMA Observatory. So this is long infrared wavelengths or short microwave wavelengths. We talked about that when we looked across the electromagnetic spectrum. Now, the other part of the picture is a wider view. And here you're seeing much cooler gas that is surrounding this star. It's the part of the picture colored blue. And what was so striking in this picture for me is that disk of gas was taking on kind of a spiral structure, which we saw as we looked out across our galaxy a few weeks ago. And the structure here is probably forming for a different reason, but it's kind of impressive to me that the same kind of structure can form for different ways as we look across the galaxy. But let's go ahead and look on across the galaxy here. So we used the full power of the electromagnetic spectrum to see what was going on all across our galaxy. And I briefly mentioned that there were two major types of galaxies if we're just looking at their shapes. We've got spiral galaxies, that's what our Milky Way is, and then we've got elliptical galaxies. Now that's not a hard and fast rule. There are also a lot of strangely shaped galaxies without the clear structures that would fit into those other two categories. So front and center, I'm showing you kind of a typical irregular galaxy, or you might hear them called peculiar galaxies in some cases. But, in general, if we run into a huge collection of hundreds of billions of stars, their planets, clouds of dust and gas, black holes, neutron stars, all the other things that we've talked about, we're going to recognize such a collection as a galaxy. So I hope you'll forgive me for not taking you through a tour of every single galaxy in the universe, because there really are a lot of them. But still, with each individual galaxy, they're all just following the same laws of physics that we've seen here in our solar system. It's gravity that determines how these galaxies interact, and they really do interact. When two galaxies are close enough together, they'll feel gravity, their mutual gravity, and gravity from one galaxy can distort the structure of another, and creating what I think are some of the most photogenic objects in the universe. These interacting and in some cases merging galaxies are pretty fascinating to look at. And we've got one right here nearby. Our own Milky Way galaxy is undergoing multiple interactions. There are small dwarf galaxies very close to the Milky Way that have influenced the structure of our galaxy. And then our closest large neighbor, another spiral galaxy called Andromeda. I guess I'm hiding part of it there. They're close enough together. The gravity is actually pulling these two large galaxies together. So give it another 4.5 billion years or so, and we'll be living in an interacting galaxy. So Milky Way and Andromeda are approaching each other. In a little over 4 billion years, they're going to make their first close approach. Now, galaxies are not solid objects. Remember, they're collections of smaller objects. So, one isn't going to destroy the other, leave a big crater behind like we see on moons and asteroids in the solar system. Here, it's going to be the grand structure of these galaxies. It's going to be disrupted. They'll probably pass through each other a couple of times. Individual stars and planets won't collide, but the galaxies will slowly merge together and create one of those large elliptical galaxies. We think most elliptical galaxies are the result of mergers like this. So it shouldn't be a huge surprise to learn that if we were to look around this map of nearby galaxies, we'd see a lot of spiral galaxies around. Like you might be able to pick out some of those shapes on your screen now, but not so many elliptical galaxies. Some 3/4 of the galaxies in the local universe are spiral galaxies, less than 5% elliptical galaxies. The balance are those interacting galaxies and irregularly shaped galaxies. So, galaxies interesting. And there are many of them. Adding to your screen now, one of the most complete 3D maps of the universe available today. A few different large surveys being displayed here. Altogether, I think, if I counted all the dots correctly, over 4 billion galaxies going to be appearing on your screen. And even on this large scale, you can pick out some structure. It's not just a formless blob of galaxies. There are some big empty gaps on our map here, but that's not because there aren't any galaxies there. And that's just because our own galaxy gets in the way. If I grow the Milky Way to gargantuan proportions, you can see that the spiral arms of our own galaxy just block our view of the universe beyond. Despite all of our powers, looking across the entire electromagnetic spectrum, we just can't map those parts of the universe. But then in other parts of the universe, you can maybe still pick out some other structure. Like there are parts where the dots are closer together, so it looks brighter on your screen. And then there are areas where there aren't so many galaxies. Galaxies are arranged in groups and clusters, just like stars can be. And then there are huge empty voids where we don't find very many galaxies. There's another thing, too. All the galaxies are moving. Just like stars are in orbit around the centers of their galaxies. I showed you the orbits of stars around the center of the Milky Way a couple of weeks ago. But all the galaxies are moving, and we can trace that the same way that we trace the motions of individual stars. A few weeks ago, I showed you how we can watch the motion of individual stars to pick up the signal of planets in orbit around those stars. It's called measuring the star's radial velocity. We can see the stars get closer to us and move farther away. Well, we see that with galaxies too, But in almost every case, aside from nearby galaxies like Andromeda, the other galaxies are getting farther away. So that suggests to us that it's not just that all the galaxies are individually moving away, it's that the entire universe is expanding. And it's expanding at a pretty fast rate. We'll get back to that. But I do want to quickly address here the fact that it kind of looks like the Milky Way is at the center of our map. But I assure you it is not the center of the universe. Even though it looks like all the galaxies are moving away from us, it would look the same no matter what galaxy we lived in. I made a little illustration that I hope explains this. There's something like the Milky Way at the center of your screen. You've got many galaxies in all directions, and I'm just making the universe expand, so all the galaxies appear to be moving away from the center of the screen. All right, so that's what we see in the real universe. Let's reset the picture, but let's move to another galaxy. Now, if the universe begins expanding, just like before, the galaxy we live in is still stuck in the center of the screen, but all the other galaxies still moving away from us. So that's something of an optical illusion that works the same way no matter which galaxy you live in. So we aren't the center of the universe, and all galaxies are moving away from all other galaxies, at least on large scales. But wait a second. If all the galaxies are moving away from all the other galaxies right now, as we move forward in time, what if we look backwards in time? Well, you go backwards in time, all the galaxies are going to get closer and closer and closer together. You run the clock far enough back, and that suggests that at one time, all the galaxies were much closer together, all the stars in the universe were much closer together, all the stuff in the universe was much closer together in the far distant past. In fact, you go far enough back, and everything in the universe would be so close together that it would be more like the inside of a star. I showed you this view of the inside of the sun a few weeks ago, and I mentioned that individual bits of energy, individual photons, can bounce around inside the sun for a million years before they escape and travel through the solar system. Well, in the early days of the universe, it was the same way. Energy just bounced around. It couldn't travel freely through the matter that made up the universe. It wasn't until the universe expanded far enough that light could travel freely and created a wave of energy that we can still see in the universe today. If I back away from the Milky Way far enough, we will be able to see what is called the cosmic background radiation, or the cosmic microwave background. This was originally high-energy gamma radiation when it initially traveled through the infant universe. This was about 380,000 years after the Big Bang. But in the last 13.8 billion years, the universe has expanded enough that this energy, this light, has been stretched into the microwave part of the spectrum. So that's the way we see it today. In fact, we are able to see it today, and the fact that we see it at the wavelength, at the temperature that we see it today, it gives us important information, like the age of the universe. That 13.8 billion year age I just gave you isn't a coincidence. We know that from this background radiation. The slight color variations you see on your screen are because that radiation was first traveling. The way it traveled changed based on small temperature variations and then small density variations in the infant universe. And those small changes in this first light of the universe we're able to see today is what led to the large-scale structure that we saw across the universe. So those big clumps of galaxies and those big empty voids between galaxies, and that's all because of those slight color variations you see on your screen here in the cosmic background radiation. So that was pretty painless. In about 20 minutes, we got all the way from Earth to the edge of the universe. And no big surprises, right? Our solar system gave way to planetary systems across the galaxy. Our galaxy gave way to other galaxies. The structure in our galaxy, those spiral arms, could tell us about how galaxies are interacting with each other, and then we traced it out to the structure between the galaxies, which was imprinted in this ancient light from just after the Big Bang. The universe isn't so complicated when you get right down to it. There's just one small thing missing from this picture. Let's think all the way back to the solar system. We saw the planets arranged in their orbits around the sun. And of course, all the planets go around the sun at different speeds. They each have their own individual orbital rate. The closest planet to the sun, Mercury, goes faster than Venus, which goes faster than Earth, all the way out to Neptune. So this orderly progression in the orbital speeds of the planets is just following the universal law of gravitation. This is how planets work in all planetary systems. It determines things like the periodic launch windows for spacecraft moving from Earth to Mars. You don't want to go when Earth and Mars are on opposite sides of the solar system. As we saw last week, you wait until the planets are a little more closely aligned on one side of the solar system. So that makes sense. We can see that all across the Milky Way. But it gets a little bit different on the scale of galaxies. If you look at stars across the Milky Way or stars in other galaxies, we see they don't follow this same pattern. In fact, stars farther from the centers of their galaxies can actually move faster than stars closer to the center. So the opposite pattern we see in the solar system. We see the same thing happening in clusters of galaxies as well. The arrangement of the galaxies and the motions of galaxies inside their clusters suggests that either objects at these scales aren't following the laws of physics, which seems unlikely, or we just aren't seeing the full picture. So the best explanation we've come up for this so far is that there is some more stuff in the universe, that despite our ability to look all the way across the spectrum from gamma rays out to radio waves, we just haven't been able to see directly. We think that this material, called dark matter, is actually more common in the universe than the regular baryonic matter that you and I and stars and planets and asteroids and galaxies are made out of. In fact, there could be 4 to 5 times more dark matter in the universe than that normal baryonic matter. So that's surprising enough. But I was drawing a pie chart for you on the screen there, and most of it is still empty. Here's one more little problem with our picture of the universe. I showed you that all the galaxies were moving away from each other. The universe is expanding. Fine, that's the result of the Big Bang. But the gravity of everything in the universe, all this matter, both normal and dark, should be slowing that acceleration down, and perhaps the universe would eventually collapse again. But our best measurements show that the rate of expansion is actually accelerating. So that's not following the laws of physics either, unless we had some other form of energy powering this expansion. That as yet undetected energy is called dark energy, and in terms of the total population of the universe, it makes up about 3/4 of everything in our universe. As Einstein famously showed us, E = mc squared, so mass and energy are related. So this pie chart really is the total population of the universe we live in. About 3/4 of it, invisible energy. Another 20% or so, invisible matter. And the last 5% or so is all the stuff we can see, touch, taste, smell, hear. That's in that tiny yellow sliver. So I guess the real takeaway here is that if I were truly going to show you everything in the universe, all of these shows I've done over the last 12 weeks would have needed to be 20 times longer, and most of the time you would have been staring at a blank screen. Or maybe that's the possibly relieving fact of the day. I didn't show you all that dark matter and dark energy along the way, but it does make up most of the universe that we live in, so it's an important part of the universe. We're just still struggling to figure out exactly what it is made out of and how we can measure it directly. But measurements, what we can see, suggests that it really is out there. So there you go. The whole universe in, just a few painless months. Now, just because we have achieved the goal that I originally set for myself 2 months ago, or 3 months ago, that would be 12 weeks, that doesn't mean that we are going off the air. These shows are going to continue, but we're going to chart slightly different paths each week. So here is what I propose. A few months ago, we collected a number of questions that we originally intended to answer in a series of short videos. But as time has gotten more and more limited in recent months, those have kind of been on the back burner, and not many of those answers have been released. So next week, I am going to go back into the archives, pull out a bunch of those questions, and answer just as many as I can. Then, if you think of more questions, if you've got questions after seeing this week's show, or if in the next few days you think of more random space questions, return to the recorded version of this show in our video archive here on Facebook. Add those questions to the comments as well, and I'll add those to the list. After all, we're in this together. Both living in the universe, and the pandemic, and finding quality edutainment. So, there are a few things that each of us individually can do to make this situation a little bit better on everyone involved. In the latter case, it's just bombarding me with your questions and requests. If there's something in space you really want to see, just let us know. Add it into the comments, and I'll try to include it in a future episode. For now, I'm going to complete our flight home from the edge of the universe. It may take me just a few seconds to get there, so I'm going to leave the video stream up here for a second. But if you do think of questions, again, leave those in the comments. And until next week, I just want to say stay safe out there, and thanks for watching.